Hello, so welcome back to another class. So we will still be discussing about vertical motion, but we will be doing some different problems. So let us just have a look at the first problem. A particle is projected vertically upwards with a velocity u in a medium whose resistance per unit mass is proportional to the square of the velocity. If capital V is the terminal velocity and m is the mass of the particle, show that when the body has fallen back to the point of projection, the loss of kinetic energy is half mu square u square over capital V square plus u square. So that is what we want to prove. So what is happening over here is we are having a body that is projected upwards with velocity u. So it will come back down and then it will have some velocity when it comes back down. Okay, the velocity will no longer be u. Okay, this is when for the upward motion, but when it is coming back downwards, the velocity it is maybe small v. The velocity at the highest point is 0. So what is happening over here? First of all, the velocity decreases to 0, and then from 0 it again increases to v. Okay, maybe from O to G. Okay, I will name this one as G to denote that it is the greatest height. Okay, so the velocity over here is 0. So what we will do in this case is we will divide the motion into two parts, the upward motion as well as the downward motion. And then we will find the change in the kinetic energy. We will see whether there is a loss in kinetic energy or whether there is a gain in the kinetic energy. But according to the question, there should be a loss in the kinetic energy. How will we know that there will be a loss in kinetic energy? When we see a minus sign. So that is what is expected. When we find the change in kinetic energy, we should expect that there should be a minus sign. Okay, so let's try. Okay, I will do the downward motion first and then I will do the upward motion. Why will I be doing the downward motion first? Because we also have terminal velocity. Okay, so let's see. For downward motion, in fact, I can even do it side by side. Okay, so you will see what is happening. And for upward motion. So the equation of motion is for the downward motion it is m d2x dt square, because the particle is of mass m, it will be mg minus mkv square, because the resistance is proportional to the square of the velocity. Similarly, over here for the upward motion, it will be md2x dt square equal minus mg minus mkv square. So as you can see, for the downward motion, the particle is moving down, the gravity is downwards, whereas the velocity, the resistance is upwards. So that is why this one is opposite to the motion. So that's why we will be having a negative sign, which is this. This is for the resistance. Whereas for the upward motion, the particle is moving upwards, the weight it is downwards, and the resistance it is also downwards. That's why we will be having both negative signs over here. We can actually cancel m from everywhere, so we'll be having this. So at terminal velocity, capital V, the acceleration for the downward motion will be 0. You'll be having g minus k capital V square. So this is what we will be having, or in other words, g will be equal to kv square. Okay, so this one we can use it over here, we can as well use it over here. Okay, because the terminal velocity is always calculated by using the downward motion. So now what we will do, we will substitute this one over here. Okay, hence for both x dt square will be minus g will be minus kv square. Okay, we can take common k, we'll be having this, and over here we'll be having g, which is kv square, k v square minus small v square. So this is what we will be having for the downward motion, and over here for the upward motion. But now comes our choice. Should we use dv dt or should we use dv dx? Okay, so this is very important. This choice, whether you should use dv dt or v dv dx, it is very important. Over here we will be using v dv dx because the distance, it is fixed for the upward motion as well as for the downward motion. It is the same distance, which is h. Alright, so this is what will happen. Okay, we can denote it with h for the greater side, whereas over here what should we be considering? For the downward motion, the particle is starting from the point 0 and it's ending over here. The height is always h. Okay, whereas if we are using dv dt, the time, we don't know whether it is the same for the upward motion, whether it is the same for the downward motion. So that's why I won't be using dv dt. I will be using v dv dx instead. So using v dv dx in both upward and downward motion, we'll be having something like this. Okay. Now we just have to separate the variables and integrate. Once that is done, okay, we are done. Okay, so over here we'll be having v square minus v square v dv equal k dx. And over here for this upward motion, again we can separate the variables. Capital V square plus v square equal minus k dx. So over here now we will integrate integration everywhere. The limits, this one is for the downward motion. For the downward motion, it is starting with velocity 0 and it ends with velocity v. It is always h, so from 0 to h. And over here it will be for the upward motion, the velocity, it starts from u, it ends at 0. At the highest point the velocity is 0, whereas over here it's still 0 to h. Okay, some of you may be confused. Why is it that over here it's 0 to h? Some of you may be thinking, okay, in one case it should be h to 0. Just remember that we are just fixing the distance to be h. For the upward motion, we are measuring the distance from this point. So that is why this point will be the 0 point for the upward motion. Whereas for the downward motion, this point is the 0 point because we are measuring the distance from this point for the downward motion. For the upward motion, we are measuring the distance from this point. For the downward motion, we are measuring the distance from this point. So that is why for both the cases it will be 0 to h. Okay, we can measure the distance from the other point, but everything, the equation of motion will change, okay, which we don't want that. Okay, so now we just have to integrate integration of this one. If you remember, there is one formula, okay, which says like this, that if you have fx and over here f dash x dx, then the integration, it will be log fx. Okay, so that is what we want to do. Over here, capital V, it is a constant because it is terminal velocity. If you differentiate this one, how much will you get? With respect to V, of course. If you differentiate it, you will get minus 2V. Okay, so we will try to get minus 2V in the numerator. We can do that by multiplying both sides by minus 2. Okay, multiply both sides by minus 2. We'll be having this minus 2kh. For this one, the differentiation of this one, it is just 2v. So we can multiply both sides by 2v dv. Over here it is from u to 0 equal minus 2kh. So this one and this one, they are equal. You can name this one equation 1 and you can name this one as equation 2. So both of them, as you can see, they are both equal. The right hand side, they are the same, so the left hand side will be the same. So you will be having this 2v v square plus v square dv. So now we just have to integrate. Okay, do not cancel this 2 because we have adjusted. Okay, so the integration of this one, it is just log v squared minus v squared, and then the limits are from 0 to v. And the integration of this one, it is again log capital V squared plus v squared u to 0. So this is what we will be having. Let's see. Now just substitute the limits. Substitute the limits, we will be having log v square minus v square minus log capital V square. Over here we will be having log v square minus log v square plus u square. So this is what we will be having. Okay, if we use the properties of logarithm, we will be having log v square minus v square upon capital V square, whereas over here we will be having this. So this is what we will be having. Over here capital V square minus v square, and over here capital V square plus u square. So now we can cancel the log. Why can we cancel the logarithms? Because logarithm, it is a 1-1 function. It is a 1-1 function. So that's why we can cancel logarithms. So we'll be having this. Oh, what actually am I trying to do? Okay, just write it down. Okay, I will explain. I am trying to get an expression for small v. That is why small v will always be to the left side. Everything else we will take it to the right side. So this is what we will be having. Okay, so ultimately we are having that v square. Okay, this one will get cancelled. Take this one to the right hand side. We will be having u square capital V square plus u square. Okay, so we have obtained v square. Okay, so this will be done. Okay, but now let us just take a look back at the question. We have to find the change in kinetic energy. Change in Ka is equal to half mv squared. This one is the final velocity. So what did we do? We are projecting it out with velocity u. It has returned with velocity v. So this one is the final velocity. So this one is the final kinetic energy minus the initial kinetic energy. So we'll be having half m v square minus u square. So it is equal to half m v square. We can substitute this expression over here. V square plus u square minus u square. okay, half m. Okay, we are actually done. Minus u power 4 v square plus u square. So as you can see, we are getting a minus sign. This one and this one will get cancelled. Minus u power 4, we can write it as half m u square v square plus u square. The minus sign indicates that there is a loss in kinetic energy. Hence, we are done. The loss in kinetic energy is equal to half mu square upon capital V square plus u square. So this is all for question number 1. Okay, so now let us try question number 2. I hope it won't take too long. Okay, question number 2 says that a particle of unit mass is projected in resisting medium, okay, varying as the velocity. Okay, t is a time interval. So what is happening? Okay. So over here what is happening is that you are throwing a particle upwards with velocity v1. Okay. At some point of time it is having a velocity v1, it is upward motion. So this is for the upward velocity. And after some time, okay, it will reach the highest point 0, O. And then after some time it will reach another point, okay, where it is having a velocity v2 downwards. Okay, t, it is the total time for this portion traveling from here to here. So what we will do, since for the upward motion we will consider the time to be t1, that it take time t1 to reach from this point to the greatest height g. Okay, and let t2 be the time taken from g to p in the downward motion. So this is what we will be doing. Again, I will write on both sides for the downward motion and for the upward motion. And it should be noted that t1 plus t2, it will be the total time t, which is in the question. T is a passage between these 2 points from O to P. Okay, for downward motion. And over here will be for upward motion. Equation of motion is particle is of unit mass, so that's why it will be 1 everywhere, g minus kv, and over here we'll be having t2x dt squared equal minus g minus kv. Okay, when the terminal velocity is capital V and terminal velocity capital V, we will be having 0 equal g minus kv, k capital V. So g, it will be k capital V. We can substitute this one over here, we can substitute this one over here, hence. But now we should be very careful. Should we use dv dt or should we use v dv dx? Okay, you can see over here that the distance, it is not the same in both the case. Okay, but we are in fact interested in the time, even though the time it is not the same in both the cases for the upward and the downward motion, but we are interested in the time. Okay, if you take a look at the question, so that's why we will be using dv dt. Hence dv dt, g you can write it as this, and over here we'll be using dv dt again, minus k v plus v. So this is what we will be having. Now what do we have to do? We just have to separate the variables and integrate. K dt, integration. Okay, we will write the limits for the integration afterwards. So this is what we will be having. Okay, integration. For the downward motion, it is from 0 to t2, from 0 to t2, okay, the time. And for the this one is for the velocity. The velocity is from 0 to v2, 0 to t2. And over here for the upward motion will be from v1 to 0, from v1, and the velocity at highest point is 0 to t1. So this is what we will be having. Next, we just have to integrate. Okay, integration of this one, it will be minus log v minus v, v0 to v2 equal k d2. So this is what we will be having, and integration of this one will be log capital V plus v, v1 to 0 equal minus k d1. So after integrating and putting the limits, you will be having this one. So next what we will do, okay, you can actually take this minus to this side so that it won't look too confusing. We can just substitute the limits, minus log v, and over here again just substitute the limits, log v minus log v plus v1 minus kt. So now what we will do is this. Okay, in fact we can write one more line so that looks simpler, minus kt2, and over here we will write this line, v plus v1 minus kt1. So now what we will do is, you must remember that t1 plus t2 equal capital T. T1 plus t2 equal t. So we will be adding 1 and 2. If we add, we will be having this one plus log v equal minus k t1 plus t2. This is what we will be having after adding equation 1 and equation 2. So we are almost done. Now again just use properties of logarithm. Log a plus log b equal log ab times v plus v1 equal minus kt. So this is what we are having. So this one and this one will get cancelled. Convert this one into an exponential, e minus kt. So we are done. Hence v minus v2, v plus v1, e minus kt. And if you remember the value of k, it is g upon v. So this completes question number 2. I hope it is clear. Okay, we will be doing some more exercise maybe next time, or maybe I will just send the notes, okay, the solve exercises as notes, and then you can have a look at them by yourself. Until next time.